que me habían hecho. O sea, tú quieres que me conecte a este mismo chat en directo a las 7 o algo así. Esa es la idea.
Sí, es lo que hacen los demás lecturers, si tienes
Vale,
tiempo.
vale. Sí, sí, no hay problema, no hay problema.
Sí, si no puedes, lo puedes hacer por como lo has hecho hasta ahora, pero...
Ayer me entró la duda, como solo vi una pregunta en el pues dije, la contesto ahí y ya está, ¿sabes? Pero no hay problema.
Es que muchos no lo escriben allí, solamente las hacen online.
Vale, pues nada. Joder, te iba a decir pas problem, tío. No da problem.
Ok, no problem.
Pas problem. ¿Qué te iba a decir? Me he dado cuenta, hay una multiplicidad de canales porque ayer no nos entendimos tú y yo. Tú hablabas de que habías creado uno, yo pensaba que te referías al que había creado yo ya, que lo había creado el día anterior. Entonces ahora mismo hay 2 canales con mi nombre o con mi tema y luego está el de los problemas. Entonces como que la gente me está escribiendo en 3 canales diferentes, ¿sabes?
¿Cuáles son?
Pues mira, a ver si me meto en esto.
Sí, tío.
Por el propio nombre los vas a identificar. El que creaste tú era GW Figueroa, pero yo había creado ya GW Early Universe Dani Figueroa y luego está el de
No lo
Discussion
veo
of
yo.
Exercises. O bueno, el que creó quien fuera. Entonces, en realidad, claro, es que ahora mismo a través de estos 3 me están preguntando cosas. Quizá habría que buscar unificarlo de alguna manera.
Puedo borrar uno, ¿eh?
No lo sé. Claro, pero si lo borras, se borran las preguntas que están ya ahí.
Bueno, igual tampoco era
Solo.
mucho, no te
Vale,
preocupes.
bueno.
So it's already 3:45 in my time, which I guess quarter to what? To
11, I believe, for them.
11, yeah. So maybe we can start already. So we are very happy to have the second lecture by Daniel Figueroa on gravitational waves. So whenever you want, Daniel.
Okay, thank you very much. Can you confirm you guys are seeing only the presentation right now?
Yes.
Okay, excellent. All right, so welcome back to the second lecture. Let us first of all recall a little bit what we looked first in the first lecture, or last in the first lecture. So if you remember, guys, yesterday or 2 days ago, we consider definition of gravitational waves, for which we gave a first approach based on linearized gravity in Minkowski. Then we consider a second approach based on a scalar vector tensor decomposition. We did it for Minkowski, but in reality, this is valid for any space-time in the background that is invariant under rotations. So certainly for any homogeneous and isotropic space-time, as it is cosmological, the case of cosmological backgrounds. Okay? And then there was a third case that we couldn't discuss based on having perturbations on top of general space-time backgrounds. But I must say that given the fact that this would take me another extra 10 minutes, I think for the time being, we are going to skip it. And if there is time at the end of this lecture or at the end of the next lecture, then we may reconsider this decision. It's not crucial, it's not fundamental at all. We already know everything we need to know, okay? So don't worry. If there is time, we'll discuss it. Otherwise, it's not so relevant. In any case, you have the discussion on this third approach in the transparencies in the website. Now, before we move into the second lecture, let me give you some perspective that we already gained based on our discussions on the first lecture. So if we want to discuss the propagation and creation of gravitational waves in cosmology, this implies, first of all, that as a background, we are going to use the Friedmann-Lemaitre-Robertson-Walker background as written here. And as perturbations, we are going to focus only in the transverse traceless part of metric perturbations, which to linear order, these are gauge invariant, as I actually showed yesterday. All right, these are this is the part of perturbations that represent gravitational waves, and is gauge invariant, which means doesn't depend on the frame we look at them. Furthermore, the equation of motion for them is a wave equation. So far in the first lecture, we discussed or we discovered the wave equation in Minkowski. Now, if it's the wave, we talk about propagation of gravitational waves in cosmological backgrounds, FLRW backgrounds. It's going to be essentially the same wave operator equation, but with a friction term here. Okay, that's the only difference, where curly H here is the Hubble rate. And notice that I'm using conformal time. hence the primes represent derivative with conformal time. And maybe the only relevant thing to point out here is that the source is naturally suppressed by G. G, remember, is the inverse of the reduced Planck mass, of the full Planck mass square. And the source is actually given by the transverse stressless part, this is what DT represents here, of the so-called anisotropic stress, which is nothing else but any deviation of the total energy momentum tensor of your system compared to the energy momentum tensor of your background. So there is an energy momentum tensor that creates the expanding background, and there is a full energy momentum tensor of your fields living in that background. Any difference is what we call anisotropic stress. The transverse stressless part of each naturally sources gravitational waves. So if I write it actually explicitly at a fundamental level in terms of explicit expression for the different type of fields we may consider, this is the result. Essentially, the kind of sources we may have are built from scalar gradients, from the gradient, spatial gradients of scalar fields. In the case of gauge fields, then you need to consider the electric and magnetic components because these are gauge invariant, and this applies for abelian or non-abelian sectors. And in the case of fermions, you have this bilinear combination with a covariant derivative of your fermion field here. Okay. Okay, so the game we are going to play in these next two lectures is the following. Knowing this master equation that tells me about the creation, taking into account a source at the propagation, when I follow how they evolve the gravitational waves, I will look for fundamental situations in the early universe, in the very first second of the universe, essentially, where I will have active sources. So non-trivial transverse stressless part of anisotropic stress in some situation that will source gravitational waves. And then we will follow them, these gravitational waves, until today, and see what are their properties and whether we can detect them or not. Okay. So we're going to begin with the second lecture. In the first lecture, we cover definition of gravitational waves in full detail, because we actually also made a detour to discuss basics of general relativity. In this second lecture, now we're going to discuss gravitational waves from inflation and from what we call the preheating stage that follows after inflation. So let me begin by giving you guys a primer on inflation. So what is inflationary cosmology? Inflation is a mechanism, very simple, which I will define in a couple of slides, which is needed in order to cure some inconsistencies of the hot Big Bang universe. So the hot Big Bang universe is the universe expanding according to a thermal plasma since some initial moment in the universe. We don't know how it came up here, how it came out, that plasma, from where. But we know that if you describe the universe like that, there are some problems. These are called the homogeneity problem, or the isotropy problem, or the H problem, sorry. And these need, they need some solution. And inflation gives you naturally a solution, since inflation predicts naturally an explanation for the cosmological principle, so for the homogeneity and isotropy of the universe. Okay, I believe Rogerio covered kind of these ideas. So I'm actually gonna rather focus more on the idea that actually inflation is a famous framework, not because it solves really these other basic problems of the hot Big Bang theory, but rather because it provides a natural mechanism to create the initial conditions for the universe. And by initial conditions, we mean the origin, the physical origin of primordial perturbations in the universe, both scalar and tensor perturbations. Okay? So all of this together constitutes the basics of inflation, and I'm going to try to explain in some detail, well, the idea behind this generation of primordial perturbations. No? Okay, at the background level, inflation, it's nothing else but a period of accelerated expansion, or if you want, a period of exponential expansion, where the universe expands at least 60-fold, which is what I'm representing here. So the universe all of a sudden blows up, scales, say from, in this given example, we had a couple of particle species separated 1 centimeter, and it blows them up a factor e to the 60 which translated in basis 10, it corresponds to 10 to 28. Okay, so initially something separated 1 centimeter became separated 10 to 28. Sorry, I'm just switching off my phone, realizing I left it on. Sorry for that. Okay, so now definition of inflation technically is as simple as considering a period of accelerated expansion. Okay, a period where the scale factor accelerates positively. Mathematically, this is equivalent of having the comoving Hubble radius, okay, the inverse of the Hubble scale, but in the comoving Hubble scale, changing, shrinking, okay, with its derivative negative. Okay, that's simple. What does it mean? It means that physically inflation corresponds to some mechanism such that at the beginning of inflation you have some kind of comoving Hubble radius. During inflation you shrink it exponentially and you make it very, very, very tiny. Then inflation ends, and then the Hubble radius, the comoving Hubble radius, grows until it matches at least our current observable horizon. Okay, it is this matching with at least our current horizon, it could be bigger, of course, that determines from observation, no, the fact that we need to match this Hubble radius today, that we need at least 60 EFOLs. And here you have the simple counting for this. Okay, you can do it at home. We won't stop now here. So we need a period of accelerated expansion for at least 60 EFOLs, which means the scale factor grows a factor e to the 60, or as I said before, equivalently of the order of 10 to 28. Now, if you have such a period of accelerated expansion with 60 EFOLs, then you solve immediately these problems of the hot Big Bang theory, the horizon problem, and also you solve the curvature problem, which has to do with the fact that nowadays there is actually the observation nowadays, since a long time, we know that the universe is spatially flat, and therefore, inflation provides a natural mechanism if you want to explain this. I do have access to the chat, so maybe
Okay.
shall I answer some of these questions? Yes.
Yeah, of course.
How inflation avoids early singularity? Okay, well, first of all, you should realize that this idea of singularity is a bit misleading, all right? Because the singularity idea is based on the fact on taking the picture of the universe expanding according to the hot Big Bang idea, which we know is inconsistent, that's why you need inflation, and then extrapolate it all the way back to in initial time where you would have this singularity, all right? But now, in order to reach that moment, you necessarily would need to go through super Planckian energy densities, which is a regime in which certainly we don't have under control our theory, because that's the regime of quantum gravity, and we don't have a prediction for that. Okay, so first of all, within the framework, there is no such a prediction of singularity. That's an extrapolation based on physics we don't know, and what is really signaling is a failure of the theory, I would rather say. Okay, now secondly, inflation, it's a mechanism that we don't know how it starts, or at least part of the inflationary paradigm is not about how it starts. It's about saying once you start inflating, so having accelerated period of expansion, then you solve the problems of the hot Big Bang theory, and then you match with all the observations. Okay, so okay, I think that addresses the first question. Second question, is there an upper limit on the number of EFOLs? Not really, but there are problems. Conceptually, you could think there are almost infinite number of EFOLs, but then in certain scenarios you run into problems. Okay, either you produce too many gravitational waves or infrared divergences in the scalar fluctuations or things of this sort. So it's a model-dependent aspect to answer that question. But let's say a priori you can have really way many more than the 60 EFOLs. Okay, and then depending on the model, you may run into an upper bound or not. Another question, is there any symmetry argument that prevent inflation to decay, inflaton to decay, since after inflation it decays? No, it's not really based on symmetry argument. It's just that in order to do inflation, you consider the inflationary sector driven by an inflaton, as we will see in a moment, very isolated, if you want, with very weak couplings, all right? But there is a number of circumstances that after the end of inflation trigger the decay of the inflaton through those couplings. And actually, we're going to see a little bit of that today, since we will cover reheating. Okay. During inflation, universe accelerating, but after inflation, why acceleration ends? Because inflation means to have acceleration. Okay, and as we will see in a moment, how to implement inflation, as we see already appearing in the slide. We typically do it with scalar fields, simply because it's very easy to to construct a homogeneous isotropic space with a scalar field in the limit where the potential energy of these scalar fields dominate over its kinetic or gradiental counterparts of energy. And the reason why we do it like that in this potential dominating regime is because then the equation of a state associated to a scalar field, which is the ratio during pressure and energy density, actually is dominated by the potential in this expression, and is close to -1. So essentially, you are close to a cosmological constant or quasi-cosmological constant, and the natural solution of the equation is to inflate. Okay, but as we will see in a moment, that doesn't last forever. Okay. Okay, this is another question. Let me advance a couple of slides, and then I will try to address it. Okay, so how do we implement with a sector of scalar fields inflation? Typically, we do it in the so-called slow roll regime, demanding that the kinetic energy of the inflaton, the guy responsible for inflation, is smaller than its potential energy, and that its accelerated motion is smaller than its friction in the equation of motion. And essentially, this can be translated into constraints or requisites in the circumstances of the potential of the inflaton. So there are these epsilon eta potential parameters defined like this, that if they are smaller than 1, they guarantee immediately, if they are smaller than 1, that these other ones above here, which are the real requisite to do inflation, they are also smaller than 1. And if they are smaller than 1, we are inflating. In particular, we are quasi-exponential expansion in a quasi-exponential expansion regime. Okay, which means that the scale factor expands like this, as written here. Now, let me see the question, but if inflation expands the space faster than the particle can move, then that makes the particle concentrated in certain region and form singularity? No, no. On the contrary, if the expansion of the universe is accelerated and it corresponds actually to a quasi-exponential expansion, you dilute the concentration of particles. Okay, so they don't concentrate nowhere, you just separate them tremendously, just think that if any two particles would be close to each other, the inflationary expansion would put them away, cosmological distances. Okay, so they don't concentrate to make any singularity. So
yes, maybe I can moderate for you the questions if you want, so you can focus.
Yeah, maybe it's better, because otherwise, maybe it's better.
You don't check the chat, so you can.
Okay, very good
for you.
Thank you. You let me know. Yeah. Okay. So very good. How do we implement inflationary scenario with a scalar field? Well, it's extremely simple. The simplest case actually we can do is m squared phi squared. So we create a potential that is quadratic in the amplitude of the field. Immediately, this tells us what are these epsilon and eta potential parameters. Okay, and we can also express the number of fifolds as a function of the field. And essentially, what we see for this kind of parabolic potential is that simply by placing the inflaton at some initial amplitude of the potential, sufficiently large, so normally these have super Planckian amplitudes, okay? Be careful, the amplitude of the field is not the same as the energy density, so super Planckian amplitudes in the field has no problem with having super Planckian energy densities, okay? So if I place it here at some super Planckian amplitude, then the field itself, just rolling its potential, enters into a slow roll regime and inflates the universe. Okay, so this answers now one of the questions that there were before. Why do we stop accelerating the universe? Because at some moment, just from the rolling, its own dynamics in this potential, the inflaton starts accelerating itself just because it gets like closer to the bottom of its potential, and it's like a harmonic oscillator. So at some moment, it crosses this critical point where the epsilon eta parameters become 1. And this implies the end of inflation and hence the end of accelerated expansion. Okay. From then on, then the inflaton is going to oscillate, and the amount of expansion corresponding to oscillatory field is actually not exponential, but it's a power law behavior. Okay. And this actually can be designed, can be engineered, not only for m²/phi², but actually for any potential of this type. Okay, so it's extremely easy to actually cook an inflationary potential. Okay. Okay, now, very good. So for inflationary scenarios, the idea is that, okay, you get some potential that you think of that can do inflation. You check that initially, at some initial condition, your epsilon eta parameters are much smaller than 1. And you have to engineer your potential. As I said, in power law potentials, this happens natural. You don't have to do anything. You have to engineer them in such a way that during 60 EFOs, this is smaller than 1 until they become eventually 1. Okay, in that moment, you finish inflation, but during that period, you have expanded the scale factor at least a factor e to the 60. Okay, this is what we need in order to fit observations. Immediately, this implies that the universe is extremely flat in the spatial sense. No, not bad. It's extremely flat. But also there is the consequence that there is no horizon problem, which was one of the problems of the hot Big Bang. So it really works very well. But as I was mentioning in the very introduction of this lecture, that's not all. Okay, that's only the background solution. The question is, you know, if that's what happens to the background, what about to fluctuations? Okay, what about if I consider there are now, let's say, spatial dependent fluctuations, both in the scalar field and in the space-time metric in which this scalar field lives? And as we will see in a moment, inflation is precisely known to be a very natural generator of primordial fluctuations. Why is that? Why do I even have to think about fluctuations? Well, the reason is because the theory of fields we have is quantum field theory. The fields are quantum. And simply what I was describing before, it was the properties of the background space-time given by the background value of the field, if you want this amplitude here. But if my field is, you know, it's how to say, enjoying quantum mechanics properties, then necessarily has to fluctuate. And there are going to be small fluctuations on top of this homogeneous background just because we consider quantum field theory, as simple as that. So if you want, we should promote to an operator our field, and then we should think as the expectation value in vacuum of our operator as the background solution I was giving before. Okay. Whereas we should consider on top of this vacuum expectation value quantum fluctuations, which are also an operator. Okay. Now, the expectation value of these quantum fluctuations is vanishing. Okay, because they're going to be symmetric up and down compared to the non-vanishing vacuum expectation value of the background. But that doesn't mean that they don't have a size. There is a variance. So there is a certain size associated to them that tells me how big typically these fluctuations are up and down, positive and negative. Okay. So, okay. The question is, can we compute this? Well, of course, yes, we can. But the first observation we have to make, okay, so now our aim is to compute these fluctuations of this deviation of the field compared to the background. But the first observation is that we don't live in a Minkowski background anymore. We live in a curved space-time, which is quasi de Sitter, which I recall you that the Sitter corresponds to exact exponential expansion. Quasi de Sitter means what I wrote before, where the scale factor grows approximately like an exponential, where the exponent is the integral in time of the Hubble rate. Okay. Okay. So what else? Very good. Now, if we are in a curved background, now this means that my degrees of freedom are going to be mixed. Because remember that in any decomposition of the metric into vector, scalar, and tensors, there are scalar degrees of freedom. And this scalar field is, as I'm saying, scalar. So this scalar degrees of freedom, there's going to be a mixture of scalar degrees of freedom between the part here in the metric perturbation and the fluctuations of the field itself. So in order to proceed properly, we need to isolate and identify what are the fundamental scalar degrees of freedom, and if you want, gauge invariant degrees of freedom. Okay. So we're going to start doing similarly as we did yesterday. So a general metric decomposition such that we have a background metric. This background metric is the one sourced by the background field. And then we have the perturbations on the metric, which we are going to decompose as we did yesterday. So this is the same as in Minkowski, just in a Friedmann-Lemaitre-Robertson-Walker background now, where we'll have fundamental scalars, we'll have some vectors, and we'll have some tensors. Okay. Let's zoom in now into this expansion, and let us recall actually that these vectors here, or the tensors, actually can be decomposed in a more precise manner, exactly the same way we did just 2 days ago for in the case of Minkowski, as follows. So, for instance, this vector perturbation, it can be decomposed as a gradient of a scalar minus a pure vector. Well, remember that pure vector refers to divergence-less vectors. Okay, so this vector is such that if I take its divergence, it's 0. Okay, so it has only 2 components, 2 degrees of freedom, whereas here there is 1 in the scalar. And the same goes for this tensor. I can decompose it into double spatial derivatives over another scalar, 1 spatial derivative over some pure vector, and then pure tensor. Well, remember, the pure tensor corresponds to transverse traceless degrees of freedom that we do identify with gravitational waves. Okay? Good. Now, it turns out that if you solve the perturbation, the equations for the dynamics of the vector perturbations, the pure vectors, what the equations tell you is that they decay as 1 over a. And since now we are in inflation and we are inflated exponentially the scale factor, this means that any vector perturbation that we could produce due to quantum fluctuations during inflation dies away exponentially. Okay, so we don't need to care about them. However, what about the tensors? Well, the tensors are there, okay, and as we know, they are gauge invariant, and then there are also the scalars. So all in total, in reality, we have seemingly 5 degrees of freedom, fluctuations of the scalar field, and scalar components of the fluctuations of the metric perturbations. And then we have the tensor part, the pure tensor part of the metric perturbations. Now, of course, as it happened yesterday, except for the tensors, the scalars are not gauge invariant. So if I do make a general coordinate diffeomorphism transformation of infinitesimal type, then immediately I change the amplitude of my fluctuations of the scalar field and of the metric scalar component, all right? So again, as we did a couple of days ago, one can work out what are the linear combination of variables such that we actually find gauge invariant quantities. And instead of having 2 scalars, now we have 3 scalars, no? Because of the presence of the inflaton. And this is very simple. You see this psi, for instance, that enters here, comes combined with a linear perturbation in the energy density of the inflaton. So you have to work out what is that. And this is a gauge invariant quantity. A very interesting quantity is this curvature perturbation, because this represents in reality in certain gauge the perturbation over the curvature of the background of space-time. And as you see, this is built from a linear combination of fluctuations of the inflaton and this curvature and this perturbation here, okay? And so on and so forth, okay, for these 3. So essentially, now that we have gauge invariant quantities, I could, knowing that these are gauge invariant, I could choose a gauge, for instance, one in which I put this scalar E equal to 0. Remember that scalar E is the one I'm using here through 2 gradients, and the fluctuations of the scalar field of the inflaton also vanishing. And then my metric, the spatial part, looks as follows. It's literally the delta Kronecker characteristic of Friedmann-Lemaitre-Robertson-Walker with a scalar perturbation of the curvature, so a curvature perturbation, and a tensor perturbation, okay? So we are going to adopt this scheme. We are going to consider this, this metric as written like this, with the curvature perturbation here, the tensor perturbation here, all right?
Now,
yes.
This is a question from myself to show you my ignorance, maybe. So these
Okay.
combinations that you are making that are gauge independent, these are the same that sometimes go under the name of Bardeen variables?
No, not necessarily. I mean,
Not necessarily.
Bardeen potentials are gauge invariant, but I don't recall now exactly if they have exactly this form, but it's the same idea. This is a different combination, I believe, what they do with the Bardeen potentials. But I don't have on the top of my mind their expression right now, so I prefer not to tell you yes or no because I'm not sure.
Okay.
Okay,
I remember they were built by
but it's the
doing
same idea. It's the same idea.
from the tensor and from the metric.
Yeah, that's right. It's the same idea. It's the same idea. Okay. Yeah.
Thanks.
The point is, once you identify some gauge invariants, perturbations, like I did with the curvature perturbation here, I can choose a gauge in which I put to 0 the rest, and then natural here, which it would have been a psi, psi becomes the curvature perturbation. So in this gauge, psi represents the curvature perturbation, which I know is gauge invariant, you know, and this is the advantage of using this particular gauge choice.
Right.
Okay. Now, once you have this, now we have to do a complicated operation. And of course, I'm just going to show you the result because this is complicated. Because essentially, you have expanded to first order your metric, but now we have to plug it here into the axion of our system, which contains gravity and the dynamics of the scalar field. And you have to plug in the determinant of your metric and in your rich scalar this expansion. And what happens is if you expand to first order, you will have vanishing terms. But if you expand to second order, you will have a non-trivial action for both the curvature perturbation and the tensor perturbations. These actions are actually not so complicated. I said non-trivial because they have funny factors in front, but in reality, they resemble a lot to harmonic oscillators. Okay? So what we are going to do actually is to massage them until we turn them into literally a quasi-harmonic oscillator. Okay, oscillator. So let me start with the scalar fluctuations. So you see, this is the action to second order from expanding just Hilbert-Einstein action. And essentially, it looks almost like a harmonic oscillator, except that there is this term here. So what we do is, first of all, we switch into conformal time. And secondly, we identify a term here and define a new variable, absorbing that term, okay, in multiplying the curvature perturbation. So we define this new variable, V, which is actually called the Mukhanov variable. And this is the natural variable to define such that then you are left with the action of now a quasi-harmonic oscillator. And why do I call it quasi-harmonic? Well, because there is a mass term here, okay, or a frequency term, which actually, when you write down the equations of motion, because it's not constant in time, it's just varying in time slowly, but it's not constant in time, it deviates really from an exact harmonic oscillator, okay? But it still is, yes.
There's a question from Sudipta.
Yes, sure.
It was from some minutes ago, but it fits nicely here. So he's asking, why are we using conformal time and what are the advantages of using conformal time?
Well, I'm using conformal time here because it's a natural way to write this like that. But I think during inflation, it's kind of natural to use conformal time rather than cosmic time. But you could do it in any time variable you want. In reality, I would only specialize my discussion on what time variable I use if I know the potential, okay? If I don't know the potential, like here, I'm being abstract, okay? Here, I don't know what is the explicit potential. Then I could use also cosmic time, but I decided to use conformal time. I don't think there is any particular reason, okay? Now, using conformal time, look that the mass term here looks as 1 over tau squared, the conformal time. This would be the term you would have exactly if we were in exact de Sitter. But since we are not in exact de Sitter, there is this new square here, which deviates from 3/2 just perturbatively according to the slow roll parameters. So the information on your potential of the scalar field is actually encoded in these epsilon eta parameters, okay? So Now we proceed to quantize, as we would do with any harmonic oscillator, even if this is quasi-harmonic oscillator. And the solution to this equation, in particular for the mode functions, which are the annihilation operators of my quantization, are two linearly independent solutions, are Hankel functions. We choose only one, okay? We keep only one, because there would be Hankel of first species and Hankel of second species, but only the one of first species. When we expand to sub-Hubble scales, it gives rise to this negative sign here, and this is called the positive defined frequency, so opposite to the sign in reality here, because only this exponential with the negative here gives you a positive eigenvalue when you apply the Hamiltonian over this mode function, okay? So this choice that our mode function reduces to this exponential with the negative sign here is called the positive defined frequency mode, and is what is called the Banks-Davis vacuum fluctuation. Okay, so essentially we are building our fluctuations such that in vacuum they reproduce Minkowski. That's what this means when the scales are very sub-horizon. Okay, very, very sub-horizon. Very good. So we know the functional form for every mode k during inflation. So now we can undo our redefinition of variables and compute the expectation value, the variance of the curvature fluctuation. So we plug in the analytical solution we obtain, and it essentially amounts for having this form, okay? And this is what we are going to call the scalar power spectrum. And the scalar power spectrum actually can be multiplied here by a k to the 3, so that you make a dimensionless scalar power spectrum. And now you can evaluate the form of this mode function using the Hankel properties at very, very super horizon scales. So modes that cross the Hubble radius during inflation and were stretched to cosmological scales. And the result, okay, this is a somehow lengthy calculation, it gives you the dimensionless power spectrum of this kind, proportional to the Hubble rate during inflation to the 4th power divided by the kinetic energy. Okay. Now we can do the same with the tensor fluctuations. The second order action looks similar to before, except that here we have a to the 3. We do have to do some transformations. In particular, I do a conformal rescaling of the tensor modes. And essentially now we do the same procedure. We have a quasi harmonic oscillator, and we can quantize it, find the Banks-Davis vacuum, and then build the power spectrum. Okay. The result is that I can do a dimensionless power spectrum again that evaluated at super horizon scales. It has this form. Okay, and what is the relevance of this form is that now it depends only in the Hubble scale during inflation. In other words, it depends on the energy scale of inflation. Okay, so in summary, inflation is a natural mechanism to produce a homogeneous anisotropic background and generate fluctuations of the metric, or both the metric and the scalar field system, which give me rise to a power spectrum for curvature fluctuations and give me rise to a power spectrum for tensor fluctuations, the form of which, of each of them, we can compute in the slow roll regime. Okay, the computation is lengthy. I obviously don't show it. I only give you the result. These are the final expressions of the power spectra predicted by a slow roll inflation. Now, to finish with this primer on inflation, what's the physical picture here? Imagine we plot the comoving scale, any comoving scale, versus time. So from the point of view of the comoving scale, we've removed the expansion of the universe. So what the comoving scale sees is that the comoving Hubble radius is shrinking and eventually becomes smaller than that comoving Hubble scale. So this is interpreted physically as the scale leaving the Hubble radius. But from the comoving grid, we see it opposite, okay? Like the comoving Hubble radius becomes smaller than the length, the comoving length. Then it exits the horizon during inflation, and meanwhile it stays outside the horizon, it actually gets frozen, both the scalar and the tensor perturbation. And this I will give it to you guys in an exercise. And eventually, since inflation finishes here and starts a power law growth, eventually the scale enters back in the horizon. From its point of view, comoving point of view, the Hubble radius just becomes larger eventually. And in that moment, it starts making the matter that lives in the universe oscillate, since the matter will follow geodesics according to the presence of these perturbations. Okay, end of the primer on inflation. So Essentially, in summary, inflation provides a natural mechanism through quantum fluctuations of the origin of primordial perturbations, in particular the scalar and tensor power spectrum. Now, let us understand that this power spectrum of tensor is really a stochastic background of gravitational waves. So let us again focus now on a perturbative scheme of perturbations on the metric on top of the background of a space-time describing inflation. These metric perturbations, now we focus only on gravitational waves, so we take the transversal degrees of freedom as usual, and as we just learned, there are quantum fluctuations, which means the average is 0, but there is a variance. Okay, this is a quantum mechanical ensemble. There is a variance, the power spectrum of which is the amplitude of the variance and controls actually the amplitude of this tensor being proportional to the energy scale of inflation. All right. So if we could detect this set of modes, then we could infer what's the energy scale of inflation. How do we do this? Yeah.
Yeah, there's a question related to the previous slide.
Okay.
So, by Roberto says, which type of average of the modes appear in the formula to find the spectra? Is it an average over time?
No, it's a quantum mechanical average. You should think this as a quantum field, okay, which has fluctuations. If you want, this is an operator, and then you can compute what is the 2-point function of this operator. So it really represents an ensemble average, if you want, from the classical point of view. But it is a quantum average, okay, in the sense of quantum field theory. Why was the power spectrum dimensionless? The power spectrum is dimensionless just by construction. So this, okay, let me go back here. This power spectrum, I computed here first, of the curvature fluctuation, is not dimensionless. But if I multiply by k to the 3, then this is a dimensionless construction, which is very convenient to work with, okay? So it's just, I can define, because I know the dimensions, what is the dimensionless case, okay? Now, as I said, this dimensionless power spectrum controls the amplitude of the fluctuations of the tensors and is proportional to the energy scale. So how could we prove this? Well, think of these modes now as gravitational waves that are frozen in superhorizon scales, but once they enter the Hubble radius during the post-inflationary evolution, they will propagate, they will behave as gravitational waves. So I can think of building the energy density of the logarithmic spectrum of their energy density, normalized to the critical energy density, and essentially this amounts to multiply the dimensionless power spectrum by a so-called transfer function, which is the function that propagates the tensors from the superhorizon scales to the subhorizon scales today. Okay, so how does it look, this spectrum in frequency of energy density of gravitational waves normalized to critical one? It looks like this. Here I'm plotting the amplitude of the spectrum in log scale versus frequency, and essentially the prediction of inflation is that we have a scale invariant background. So we have the same power at all the modes, all the frequencies. If I take, in reality, more careful look into the prediction, we see that there is some scale dependence here with some power law, but the power here depends on the epsilon parameter during inflation, which, remember, is very small, the slow roll parameter, in order to inflate. So there is some tilt. This is called the red tilt in a slow roll, but it's very tiny, okay? So what is the most relevant aspect of this prediction? The most relevant aspect of this prediction is what I'm plotting here is the largest possible background you could have. So essentially, the most relevant thing is that this is not observable at all with experiments like LIGO, current LIGO, or LISA in the future, okay? There is only a chance, perhaps indirectly, to measure it in the CMB. And because there is no time to cover everything, I've prepared some slides on this idea of probing these modes through CMB, of these tensor modes, at the very end of this presentation, okay? But I will not discuss it myself. So I think we are kind of on time right now. We did 43 minutes. Question now to you guys, shall we do coffee break or shall we continue inflating? Whatever you prefer.
First of all, there's a comment by Anupam, which maybe you can take. I'm not sure it's a question or an observation. So yes. Anupam is saying, Variance or two-point correlation function is inversely proportional to k cubed. So in very slow rolling region, this can be divergent.
No, that's not divergent because, you know, it really matters in what scale you are evaluating that, okay? And you see here there is a finite range of frequencies. Equivalently, there's a finite range of modes. This means that this is the highest mode, which was the last one exiting inflation. And this is above the earlier modes that left the Hubble radius at the onset of inflation in reality here. So, you know, these modes have finite numbers. So only if I would go to all the way infinite to the left, to the very infrared, okay, then I will have these problems you are talking about. So there is actually a typical problem of infrared divergences in inflation that lasts many, many IFOs, as somebody was asking me at the very beginning, okay? But if there is a finite duration of inflation, which is typically assumed, there is no problem whatsoever. You just evaluate 1 over k to the 3 in the appropriate scale, and that's it. Okay, there's one comment, Joan, you should decide. But I realized yesterday in the break we took 15 minutes, and that was the problem why I couldn't finish the lecture. So I propose we take literally 5 minutes today, and then if they want to ask questions in these 5 minutes, I'm happy to answer. Or maybe we could literally take 5 minutes, and then I answer questions at the very end of the lecture, whatever you guys prefer.
Let's take 5 minutes. I think it's a good idea.
I think it's a good idea too. Yeah,
And then we recombine at 35.
At 35, we come back, guys. Okay. See you now.
See you in a bit.
See you in a bit.
Hey, Daniel.
Yes, I'm here.
Maybe while we wait for one more minute,
Sure.
can I ask you a question? So
Yes.
about which you haven't commented, but I'm wondering whether you will comment or maybe it's a bit advanced. But one of the most striking features of inflation is the prediction that all the Fourier modes of the CMB that have the same wavelength have synchronized phases.
Yes.
And this can be nicely explained for the fact that they re-enter the horizon at the same time, and there is a oscillating equal.
Well, the explanation for this is really that they are frozen in superhorizon scales. Okay, so out of the two linearly independent solutions, one dies away, you are left with the amplitude. Yes, therefore they start oscillating in phase. That's right. Yeah.
Right. So, is there some hope of similar checks for gravitational waves from inflation if ever detected of these phase coherence?
Well, I mean, it's a slightly different the issue. So, there is the same issue of phase coherence for sure. Okay, so the predictions for the how the tensors affect the different CMB power spectra are also based on the fact that the power spectrum characterizing the amplitude is what you need, and not characterization of the velocity. Okay, so yes, it's the same issue. But besides that, I mean, the whole point of looking for the tensors in the CMB is that instead of looking at the temperature fluctuations, now you can look at the so-called B modes, which is a specific configuration in the polarization of the photon field of the CMB, which is only sensitive to vector and tensor perturbations. And since in inflation there are no vectors, then in principle, if you detect B modes, you will be detecting primordial tensors. And of course, all of that is built from the idea that you are sensitive to the power spectrum of the tensors or the amplitude because they were frozen in first place at superhorizon scales. Yes.
All right.
But I've never seen how it would look a B mode signal if there was no such a
phase coherence.
Phase coherence. I
don't
know how
that was the question, because I have seen for scalar mode how
for the temperature. Yeah, I've seen it too, but for the B modes, I've never seen it. Yeah.
Okay, that was the
question.
It
would be interesting. Yeah, it would probably destroy the coherence as well of the pattern of the CLs of the B mode. Yeah, it would probably destroy.
It's a question for consistency of the whole picture. It'd be nice to see that.
Yeah.
Anyways. Maybe we can continue because it's already 37.
Okay, very good. So maybe shall I answer these two questions that are there?
Let me see. Yes, please. Go ahead.
Okay, so the first question is about consideration of a non-minimal coupling between the inflaton and gravity. Okay, naturally, when you want to renormalize certain operators in curved space-time, and you have a scalar theory, you need to consider this kind of non-minimal coupling, which means inflaton squared times Ricci scalar. And then that comes with a dimensionless coupling in front. The question asked by Felipe is whether we could measure this coupling. Well, if I take into account the presence of this coupling, yes, depending on the amplitude, the strength of this dimensionless coupling in front, this could enter into the power spectrum fluctuations. Okay, so actually, the so-called power law chaotic models of inflation based on a power law inflaton, they don't work nowadays well according to CMB observation unless you really take into account some of this non-minimal coupling to gravity and you somehow choose the strength of this coupling to be a mild value, okay, of the order smaller than 1. Okay, so in principle, you could measure it in combination with other parameters of the potential, though. I'm not sure you can measure it separately, okay, but I'm not completely sure. Second question is why not to consider 3-point functions or 4-point functions of the fluctuation? And, well, there is actually a whole machinery of people, a whole machinery of tools to compute these 3-point functions. This is called non-Gaussianity, and 4-point functions. These are also part of non-Gaussianity. But so far, all the observations in the CMB indicate that they are compatible with almost vanishing 3-point or 4-point functions. Okay, so essentially, whatever the origin of the fluctuations, whatever the inflationary model, if you want, it's really compatible with almost free fields in the sense that mostly the 2-point function is what dominates everything. And the reason why normally we first talk about 2-point function when we are introducing inflation, because this quantifies the amplitude of the fluctuations themselves, okay? And this is what I want to give you a sense of idea here, all right? So this is why I'm focusing only in 2-point function. If we were to give a, you know, a class on inflation, of course, normally we would also take tours into 3-point function or other aspects that you can look beyond the 2-point function, okay? Okay, good. So we decided, are you still seeing my screen, I hope?
Yes.
Yeah. Okay, very good. So we decided to take the coffee break. In any case, we have to continue inflating. So what we've seen right now is that inflation predicts primordial perturbation, both scalar and tensors. And in the case of tensors, these correspond to a gravitational wave background that could be detected by direct detection if we had good sensitivity, or we don't. So there is only a chance to detect it in principle through indirect effects in the B mode of the cosmic microwave background, okay? And this is an irreducible background because any quasi-de Sitter inflationary background produces this, okay? But inflation is a very flexible scenario. And once you have determined what is the background for inflation, actually nothing prevents me from including new ingredients, such as considering extra particle species or symmetries in the game, or enhancing my scalar perturbations one way or another, or modifying gravity, or consider a bunch of other aspects, no? So let's start by this particular point, considering extra species or special symmetries in the game. So one paradigmatic example of this is so-called axion inflation scenarios. These are based on a scalar field, which is not really a scalar, it's a pseudo-scalar that enjoys a shift symmetry. And if it enjoys a shift symmetry, immediately based on this aspect, I can couple it to any topological FF dual term of any gauge sector that would exist. Maybe, for instance, the hypermagnetic whatever you want, whatever SU2, okay, that could exist, not necessarily the standard model, okay? So imagine there is an inflaton which is enjoying this shift symmetry. We couple it to some U1 gauge field, okay? Then you decompose your gauge boson into the typical two helicities of a gauge boson in the abelian case, and you study the evolution of the mode function for the two helicities. And what we discover immediately is that because this is a chiral coupling, actually, okay, this distinguishes the polarizations of the two photons, we see that in the equation of motion, there is a difference of sign for this frequency term for the two polarizations. And given the fact that there is a minus, immediately we recognize there's going to be a tachyonic mode of one of the polarizations. So one of the polarizations of the gauge field is going to grow exponentially fast during inflation, just due to the presence of this coupling, okay? So this is very nice because now if I'm producing exponentially large amount of gauge fields, they are going to act as a source of gravitational waves. As long, of course, as there is a non-trivial transverse traceless part of their electric and magnetic constructions, okay? But there is, because you are producing through a tachyonic instability, so a completely out of equilibrium distribution of these gauge fields. Therefore, there is a non-trivial time dependent and scale dependence of these guys. And if you compute their electric and magnetic fields, there is a non-trivial transverse traceless part. And whenever there is such a circumstance, we know we have a source of gravitational waves. So another consequence of having this axion inflation model is not only that we create the gauge fields like that, it's also that they source gravitational waves. And not only they source gravitational waves, they are going to produce a chiral gravitational wave background, okay? Because they only have one chirality in first place. So how does it look? The energy density spectrum of gravitational wave of this background, normalized by the critical energy density, this is the y-axis, versus frequency today. Well, here in dashed line, I'm representing the vacuum fluctuations that we discussed before, the quasi-scale invariant prediction from vacuum fluctuations. And now look what happens. There is this contribution from these gauge fields that is capable of making a blue tilt background of gravitational waves, very blue tilted, okay, which means having this positive slope. It's chiral because it's only mainly made by one polarization, and it's also non-Gaussian. There is a non-trivial 3-point function that somebody was asking me before. Unfortunately, with detectors like LISA, it's not possible in principle to detect this kind of non-Gaussianity. But in any case, if I were to ask you what is the most important aspect of the message or plot I'm showing you now here, okay, to obtain this plot, by the way, we solve this differential equation knowing the solution to the gauge field, okay? It's a complicated process, but at the end of the day, you end with a spectrum of this kind. So what is the most relevant aspect? That is observable. So now we are talking, contrary to the vacuum fluctuations background that we were introducing before, now we are talking about gravitational wave backgrounds that they sustain power in their spectrum within the capability of experiments such as LISA, okay? And they could be detected with a very high signal to noise ratio, actually. So this is observable. Okay, very good. So this means maybe if I couple other fields to the inflaton, maybe
excuse me, Daniel. Action
yes.
A question about action inflation with
Yeah.
to other variations.
Okay, can I read it out? Yeah. If we add action for GG dual term, okay, so for non-abelian case, does this ensure that we also have to add action for FF dual term as well? I mean, the symmetries allow you for it, but it really depends on the matter content you want to consider. So essentially, at the end of the day, nothing prevents you from having it, you know, because in the moment you have a shift symmetric field, you should couple it to any FF dual of any gauge sector that really exists. But depending on the strength of the coupling, you may want to consider the effect of it or not, okay? So in the example I was showing, we are only concerned with the hypercharge of a standard model, and we are neglecting, with no particular reason, GG dual coupling. But it's true, you know, even though this is not the QCD action, whatever action it is, the one I was showing before, it could not sustain a very large coupling with GG dual of SU3, for instance. So in principle, it would be kind of nicely justified to have only the electroweak sector of gauge fields. And then we should also compare the GG dual or FF dual of SU2. But again, we are just, if you want, neglecting it by hand and consider only an abelian sector, you know. Can I explain the LISA curve? Somebody else is asking. Yeah, this plot was made when there were discussion. I'm part of the LISA collaboration, okay? And for many years we've been discussing what would it be the sensitivity of LISA, because this depends on the final configuration. But the final configuration, which means distance they are going to be, at what angle, etc., was finally fixed like really a couple of years ago. And now essentially the last dashed line here, that's the final configuration for LISA, okay? So essentially the others you can just forget. Isn't the coupling to FF dual total derivatives? I think in the non-abelian case, so somebody is asking if FF dual is a total derivative. In the non-abelian case, it's also a total derivative. It's just the structure of vacuum in non-abelian case has these topological sectors, okay? But doesn't mean that it's not a total derivative. So this is the parameter. Second question, this is the parameter space that LISA can prove. Yes, this is the best parameter. This is the best case scenario in the plot I'm showing, okay? Anyway, I think I'm gonna follow the advice of Joan, as he said before. He will modulate, you tell me about the questions, okay? So because otherwise I distract myself too much.
Sounds good, but you addressed all of them already for the moment,
okay.
No?
Yeah, definitely. Okay, anyway, so I was saying, guys, so what about if we couple the inflaton with some other species? So let's think of the inflaton phi, we couple to some extra scalar field chi in this fashion. Or maybe we couple it to some fermions in this Yukawa type fashion. Or we could even think of the inflaton being a charge under some gauge symmetry, and then we have a standard covariant gauge derivative term, okay? Well, it does happen that in either of these cases, there's gonna be always, whenever the inflaton crosses through whatever privilege value we chose here, okay, which we can tweak by hand, there is always a time variation of the effective mass of the extra particles, such that we produce particles in the moment the inflaton is crossing through this special value. And the spectrum looks like an infrared window of particles excited up to order 1 occupation numbers. So if we have such a non-adiabatic excitation of field quanta, immediately we are going to have creation of gravitational waves. Now, the question is, how much gravitational waves can we produce if we have these features? And the location of the feature of the distortion of the spectrum of gravitational waves can be chosen by hand by choosing what is phi naught, okay? But it turns out for any reasonable scenario that people have looked into, that the distortion is a bump, but this bump is actually extremely small, relative in comparison to the amplitude from the vacuum fluctuations spectrum, which was already small by itself. So in other words, this is tiny, okay? So in summary, having a shift symmetry, it's a very special thing because it gives rise to a continuous production of gravitational waves, which leads to an observable background of gravitational waves, or potentially observable. Let me rather make it like that, since it's only observable for certain parameter space. Whereas if I put arbitrary couplings of other extra species, then you can produce a localized bump into an enhancement of the gravitational wave production in the otherwise quasi-scale invariant background, but it's negligible, completely negligible, okay? Okay, other mechanisms, instead of invoking symmetries or putting extra fields, is the idea that you can enhance scalar perturbations. And why is that? Because actually the observation of the power spectrum, of the dimensionless power spectrum of curvature fluctuation, comes from the CMB. But the CMB is making measurements at cosmological scales. At cosmological scales, we know that the power spectrum cannot be bigger than this 10 to minus 9. But however, nothing prevents me during inflation to have much larger scalar fluctuations during later stages to the moments when the modes corresponding to the CMB cross the Hubble radius. So those modes cross the Hubble radius 60 EFOLs before the end of inflation. Imagine we think of modes now that cross the Hubble radius during inflation 30 EFOLs before the end of inflation, 30, 20, whatever, just not 60, okay? Again, we will have to decompose our metric perturbations, but now we can realize that at second order in perturbation theory, we can build from two scalars, taking gradients, derivatives, a natural source for the tensors. So if we do have very sizable scalar fluctuations at the smaller scales than the CMB, then we could have a natural source from second order at shorter scales for the tensors. And again, we could enhance our prediction of gravitational waves from inflation. So how does this look? Well, essentially, I can take a look into the upper bound of different experiments or observations in the gravitational wave backgrounds and translate this into an upper bound of the amplitude of the scalar fluctuations in those scales. So there is a natural upper bound due to constraints of Big Bang nucleosynthesis that tell us, actually this should be a 10 to minus 6, sorry, that there cannot be more fraction of gravitational wave energy density compared to the critical one bigger than 10 to minus 6. If I take the previous formula, this translates into this second order effect cannot give rise to a power spectrum bigger than 0.1. Okay, not very competitive with CMB, that is 10 to minus 9. If I take the constraint from LIGO, I get something better, but not so impressive. If I take it from something called pulsar time arrays, then I improve a little bit because we can already give a nice upper bound on the fluctuations on those scales of the order of 10 to minus 3. And if I do it with LISA, which of course will be operating in the 30s, okay, so far it's only design, we will actually get an amazing upper bound on the fluctuations or of the scalar fluctuation, or we detect this second order effect background. And if something like BBO was ever built, then we could even do much better and go to 10 to minus 7, okay? So you see, either we detect something or we put a stringent bounds on the scalar spectrum at those shorter scales. Now, if this power spectrum of curvature fluctuation is very enhanced, you could also produce primordial black holes. I'm not sure if Francesco have already talked about them, but you know, first of all, LIGO may have detected primordial black holes. We don't know. We will determine this rather soon by measuring mass spin distributions. Okay. As of now, I think it rather looks that they are mostly astrophysical. And more interestingly, maybe, is that primordial black holes could be a candidate for dark matter, and this is the point where that I'm not sure if Francesco has already talked about. And this is very interesting because even if they are not the full dark matter, they could be still a fraction of the dark matter. And if that's the case, there are a number of effects that you could look in this case, like what is the gravitational wave from second order scalar effects, what is the non-Gaussianity due to having primordial black holes, what is the spectrum of anisotropies in the background of gravitational waves, and etc. You see, there is a number of things that you can look into, and people are actively working into this. Okay, so far we've been talking about inflation. Okay, and I was considering scalar perturbation, extra species, extra symmetries, etc. Now we are going to finish inflation and we are going to move into reheating. Reheating is the period that matches the end of inflation with the thermal era of the hot Big Bang theory. And we will see it gives very naturally to a new production of gravitational waves. So inflation ends. Okay, this is a schematic picture. This is a schematic picture of inflation, stretching exponentially the universe. Inflation ends, and now suddenly, yes, Joan?
Yeah, I'll pass you before you enter into reheating. So there's a question, maybe it would be better for Francesco, in fact, because the question is, why primordial black holes can only be a part of dark matter?
Okay, because primordial black holes, because they are finite size objects, they have a number of consequences. And there is a lot of search for the consequences of the presence of compact bodies all over the universe. And there are plots that tell you that in most of the ranges of masses, they cannot be the totality of dark matter. Okay, so primordial black holes, if they exist, they are naturally a dark matter candidate. But for them to be the full amount of the dark matter, nowadays there is essentially only a couple of windows in the mass range in which those masses are compatible with being the totality of dark matter. And for instance, the window of the masses probed by LIGO and Virgo, this is not open anymore for them if they were primordial to be the full dark matter. Okay, and this has been quantified only in the last 3 years, essentially. Okay, now maybe I turn into reheating. We change gears, so inflation has ended. We have a tremendous amount of energy stored in the inflaton, and this energy has to decay into particle species. And these particle species will decay into other particles, and they will interact among each other, and through interactions, they will thermalize, and then they will enter into a thermal universe picture, okay? So essentially, reheating is the period that matches the end of inflation with the standard thermal universe, okay? Okay, how do we study this? Well, let's consider the simplest scenarios. Let us consider an inflationary sector by a scalar field, an inflaton, maybe quadratic, maybe quartic potential, okay? By themselves, they are ruled out like this, but for the sake of the discussion, let me have them here. Then we consider extra field, say another scalar, maybe with a quadratic potential, maybe with a symmetry breaking potential, whatever you want, no? And then we couple, we make them talk through this simple symmetric coupling that requires no mass scale, okay? Well, even these scenarios, which are the simplest of the simplest, are extremely difficult to study because you have to study, on the one hand, the dynamics of the inflaton after inflation, which typically consider of damp oscillations dictating the expansion of the universe. And on top of that, you have to study the fluctuations of the inflaton and the fluctuations of the other matter field. All of these systems are nonlinear in the equations. So altogether, you have to study nonlinearities, which correspond actually typically to non-perturbative effects, as we will see in a moment, okay, and far away from equilibrium. So it's extremely difficult, and this requires typically lattice simulations, and as we will see in a moment, okay? But now let me make a remark. It is the fact that these effects are non-perturbative, so they cannot be described with typical Feynman rules of perturbative quantum field theory, that we talk about preheating with P, okay? So reheating with R is the whole stage in which we produce particles until they thermalize. Preheating with P is the initial stages of reheating where there are non-perturbative effects of the kind I'm going to explain in a moment, okay? let us focus on the simplest scenarios, chaotic scenarios, where you have a power law potential for your inflaton. So your inflaton is slowly rolling here, and at some point, it's gonna stop inflation, and then it's gonna start oscillating around the minimum of the potential, okay? But now there is a chi field, another scalar field, coupled to the inflaton, and if you redefine the appropriate conformal with this chi field, now I call it X, this is the equation of motion of the mode function of this chi field, that they have a time-dependent mass through its coupling to the inflaton. So what happens is when the inflaton, which is almost a harmonic oscillator here, whatever the shape of the potential, okay, it's not harmonic, but it's oscillator for sure, whenever it crosses through zero, it will excite the modes of the chi field, of the matter field, just because the variation of its effective frequency will be non-adiabatic, okay? Therefore, it cannot be that it behaves as a adiabatic oscillator, as a quasi-harmonic oscillator. It will behave as something else that is excited. And this actually corresponds in quantum field theory to particle production, to non-adiabatic particle production. So typical picture of this particle production is that the occupation number of a given range of momenta, typically in infrared window, grows exponentially fast with the oscillations of the inflaton. As the inflaton goes oscillating, it passes back and forth through the minimum of its potential, and every time it passes, it creates more particles through this effect, but now it builds them on top of the previous ones, so this is actually a resonant effect. This is called parametric resonance. Okay? In another type of multi-field scenarios, okay, just to change gears, you could think of an inflaton that rolls along this valley, okay, let's call the inflaton phi, then the inflaton eventually crosses a critical value, and then if we couple the inflaton to some other scalar that has a symmetry breaking potential, as described here, when the inflaton becomes smaller than this critical value, it's going to trigger a tachyonic mass in the symmetry breaking potential, the symmetry breaking guy, in the other guy. So this other guy, let me call it Higgs for simplicity, could be the Higgs of the standard model, could be another Higgs-like field. It will feel this tachyonic instability and it will grow in this direction exponentially fast. Okay, so essentially the amplitude of the modes of this Higgs field, and therefore its occupation number, will be exponentially fast depending on the mode. Okay, so only for a certain infrared band of momenta, of course. And actually, this corresponds to a phase transition, as we will discuss in the last lecture on Friday. So, what is the physics of preheating? Okay, and I insist on putting the P because these are non-perturbative effects. The physics of preheating corresponds to studying time-dependent oscillators for the mode functions of scalar matter fields, whether these square frequencies are tachyonic or simply periodic. This depends on the scenario. But when you have such an effect with tachyonicness or periodicness, essentially what happens is that a specific range of momenta, the amplitude of the fluctuation of the fields and hence their occupation number grow exponentially fast. Okay, they suffer instabilities, and this is what is non-perturbative. The growth of this particle production cannot be captured in a perturbative expansion of quantum field theory. It has to be studied by non-perturbative effects of the kind I'm describing. Now, imagine you have this instability, so the amplitude of your fields grow exponentially in a specific range of momenta. This corresponds to very inhomogeneous distribution in real space, because if only a special cases are amplified, then you translate this into reciprocal normal space, and this means that there is typical length scales of the inhomogeneous distribution. It corresponds to very large energy densities and moving at the speed of light. It essentially looks like this, these instabilities in real space. Here I'm plotting the amplitude of a Higgs field in 2 dimensions. Okay, I take a 2-dimensional cut of 3-dimensional space, and we see instability going up. Eventually, it gets inverted, this instability, and then at the end, we see the collision of all the instabilities happening everywhere. So this is a natural efficient generator of gravitational waves. Okay, very efficient generator. Obviously, because we are producing very large time-dependent anisotropic distribution of matter fields. Since the dynamic is so nonlinear, we have to do it in the lattice. Okay, how do we do this in the lattice? Well, first of all, we have to describe the dynamics of the scalar fields. Now, because we are in a semi-classical regime where the occupation number of them are very large, essentially what we can do is to resolve the classical dynamics of their Klein-Gordon equations. through their potentials, they will be coupled, so they will transfer energy from one to another, and they will evolve according to their dynamics. At the same time, we solve for the expansion of the universe through the volume average of the pressure and energy densities built by all the matter fields we have, the inflaton, the preheat field, etc., whatever we have. And at the same time, now we can study on real time in every position of the lattice what is the evolution and production of gravitational waves as sourced by the transverse stressless part of their anisotropic stress, which is nothing else but the spatial gradients of the scalar fields. Okay, so we solve all of this together in the lattice, and this is what we get. First, I show you some animation. Here, this is the case of a hybrid preheating scenario where the inflaton is coupled to a symmetry breaking field, a Higgs-like field. Okay, so here on the left, we are going to see two-dimensional slides of the Higgs with the amplitude of the Higgs in the z-axis. And here we are going to see the corresponding two-dimensional distribution of energy density around the spatial locations of the Higgs symmetry breaking. Okay? So as time goes by, the Higgs starts developing bubbles, okay, which is the growth of the instabilities. So we see that there are more acute gradients around certain regions, and hence the gravitational waves, which follow the gradients of the field, are also more acute in the same regions. Okay, this is the energy density of gravitational waves. As the Higgs continues to break spontaneously the symmetry, going towards the true vacuum expectation value, the bubbles grow, the total amount of energy density of gravitational waves grow, again, maintaining this very special localization of the energy density of gravitational waves. Eventually, the bubbles stop growing, and they merge, they collapse, they collide among each other. So essentially, the whole distribution of the Higgs breaks apart into smaller structures, and then this gets translated immediately into the energy density of gravitational waves, which now picks up shorter wavelengths and stops growing exponentially as it was doing before. Okay, so at some moment, the energy density of gravitational waves is not growing anymore, but is reflecting its spatial distribution, the spatial distribution of the Higgs, which eventually will relax towards equilibrium and will homogenize. The same for the energy density of gravitational waves. Okay, but here is an example on real time of the production of the actual gravitational wave emission due to the fact that we are following dynamically the symmetry breaking of a Higgs field through its tachyonic instability. Okay. Okay, how does it look this if I plot you the energy density spectrum of the gravitational waves normalized to the total energy density in that moment? Well, we see that initially there is a tachyonic growth following the tachyonic growth of the Higgs modes. There is an exponential growth of the amplitude of the gravitational waves. When the bubbles starts colliding, this is when the system becomes fully nonlinear, we start propagating power through the nonlinearities into the higher modes of the system. And eventually, the growth of the amplitude of the power spectrum saturates and stops just because the field dynamics start relaxing and you don't produce any more actively gravitational waves. Okay? So what is the parameter dependence of these backgrounds of gravitational waves? Typically, the energy density spectrum of gravitational waves at the time of production, so normalized by the total energy density at the time of production, they look as a single peak, like this. Okay, this is again the evolution in time of a whole event of producing gravitational waves. And in the case of chaotic scenarios, chaotic means just to choose a power law for the potential of the inflaton, the amplitude of the single peak of the maximum is just controlled by one single parameter, which is the so-called resonance parameter. And this resonance parameter controls all the physics related of the problem, the strength of the coupling between the inflaton and the extra preheat species, the amplitude of the inflaton, and the frequency of the oscillations of the inflaton, which depends on the potential of the inflaton. Okay, so if you know this resonance parameter, because you know your potential, your coupling, and your initial conditions at the onset of oscillations, then you can predict what is your background of gravitational waves from these effects. Typically, they are very large backgrounds, okay? Omega gravitational waves today, 10 to minus 11 is considered very large, but they always peak at very high frequencies, just because we are probing these scenarios at very high energy scales, okay? Which is a pity, because if they were at lower frequencies, we could look for spectroscopic effects. So we could do a spectroscopy of particle couplings, because if there were several preheat species coupled to the inflaton, each of them with different strengths in their coupling, since the peak of gravitational waves from each of them scales like this with the resonance parameter, and the resonance parameter depends on the coupling strength, essentially we'll have different peaks for the different particle species. Unfortunately, because they are at very high frequencies, there is no detectors, which there is not even the idea of any technology to measure these amplitudes at these frequencies. So there is not much to do. I'm very much afraid about this so far, at least. In the case of hybrid inflation models, where there is tachyonic instabilities, well, you can also parameterize your signal. They can also be very large in amplitude, omega gravitational waves today, of the order of 10 to minus 11. For natural values of the self-coupling of this fixed field, like natural values, like for instance, what we have in the electroweak sector of a standard model, this background would be very high frequency peaked. So essentially, again, not observable. We can tune the self-coupling of this Higgs-like field. So this wouldn't be obviously the Higgs of the standard model. And then you could shift it to frequencies like of the LIGO observatory, LIGO experiment. But of course, this is a fine tuning and it's not really well motivated to have such a small but precise number for your self-interaction. So realistically speaking, I think it's also very, very difficult to observe these backgrounds, I'm afraid. Okay. And with this, I think I'm going to conclude this lecture here, slightly before time. Just to summarize, reheating is early stage. Reheating is the production of particles after inflation. When these particles thermalize, we match with the standard hot Big Bang picture. But typically, this production can go through non-perturbative effects in the presence of couplings to scalar fields. And this gives rise to a very, very large gravitational wave production. Okay. Tomorrow, we will continue now talking about phase transitions, about cosmic defects. And we will see that, as I mentioned before, one of the cases of preheating is actually a phase transition. So actually, we will continue also talking about phase transitions for a short while. Then we will move into thermal phase transitions. And then finally, we will discuss cosmic defects. Not tomorrow, but on Friday. Sorry, I always forget that it's every 2 days our lectures. Okay. I think I will stop here today. And of course, I'm very happy to continue answering questions if you guys have more.
Thank you, Daniel. So let's see. I think the last question
from Jenny.
From Jenny. You can explain again what is the function of the source.
Sorry, Jenny, could you elaborate? What do you mean? Can you use maybe your mic to go faster? I'm not sure what you mean. What source are we talking about? Or type it if you want.
Okay, so Jenny, if you can clarify to Daniel the question. In the meantime, maybe you can answer the rest.
Okay, so another question, which parameters give frequency of gravitational waves? Well, I mean, that question should be addressed in a specific model, no? So if you have a model, for instance, of parametric resonance, okay, let's have a look. What kind of scenarios have we been looking into here? So imagine I have a model where I choose my potential of the inflaton like this, quadratic, and then I have a coupling of this kind, okay? So call it M instead of mu, okay? And let's call this coupling G, okay? Let's imagine this. So now I go to the master formula for parametric resonance for the gravitational wave production. And the peak of this spectrum, by the way, the explanation of this parametrization, how to do this computation, you can find it in this paper, okay? Here, obviously, we just don't have time to go through the full details, but you do lattice simulations, we adjust the peaks for different models, and here, essentially, what controls the final amplitude is this so-called resonance parameter, which you see, it depends on the amplitude of the coupling, or the strength of the coupling, the amplitude of the field at the onset of oscillations, and the frequency, which would be this m squared. And now you are asking me, what controls the frequency? Okay, what controls the frequency is the fact that we are in a very high energy scale model. So essentially, your frequency today, I don't have any expression, unfortunately, here, but your frequency today, to determine this, it's controlled by how high your Hubble rate it is at the time of production. And in these scenarios, the Hubble rate at the end of monomial potentials for inflation, it's very large. The energy scale is for the order of GUT, of Grand Unified Theories, 10 to 16 GeV. And the Hubble rate, that means is of the order of 10 to 13 GeV. So if you translate whatever the scale corresponding to 10 to 13 GeV into Hertz today, this corresponds to this 10 to 8, 10 to 9 Hertz. Okay, so it's the energy scale what controls the frequency of gravitational waves today. Okay, okay, Ganesh, please. Maybe, so I definitely think it's better if they can use their mic to ask the question, no? So everybody gets a clear sense. So Ganesh, do you want to ask out loud your question?
Yeah, there is the option of raising the hand, so everyone is welcome to do that.
But even can they unmute themselves directly, or?
Yeah, of course.
Yeah.
So you understand the question of Ganesh now, Daniel?
Okay, this is very general, so I'm not sure. You see how
I see, because he's not mentioning which inflationary model, no?
When inflationary model can be failed. So what failure are we talking about, and what does it mean that failing leads to alternatives? You know, so I think, yeah, guys, I would encourage you to ask with the mic. Honestly, don't be shy.
Yeah, Ganesh, I think it looks like a very interesting question. Also the same of Jenny. So guys, clarify, and I'm sure we all will learn from the question and the answer. So
yeah.
In the meantime, let's go to Sudipta question, maybe.
Okay, so Sudipta is asking why, okay, I'm gonna read here. Why vector fluctuations are not there? Can you explain again? Okay, yes, sure. So remember that in general, any metric can be decomposed into a scalar, vector, and tensor, okay, the metric perturbations, right? So this is the general expression here. Now, what happens is that if you study how these vector perturbations propagate, imagine you create them through quantum effects, which actually is believed to be the case in inflation. But once you create them, they decay as the inverse amplitude of the scale factor. And the scale factor changes a factor e to the 60, at least in inflation. So just imagine you create vector perturbations at the scales of inflation, they decay a factor e to minus 60, which is the same as 10 to minus 28. And this is why they are completely unobservable in inflationary case. For instance, in the case of topological defects also create after inflation, once you produce topological defects, if they happen to exist, no, in a phase transition, which is not guaranteed, but if they do, they also create a scalar, vector, and tensor perturbations. And however, topological defects can give support to the vector perturbations because they regenerate them continuously as the expansion goes on. So for instance, when we look into the CMB, looking for the perturbations due to topological defects, we actually look into both all scalar, vector, and tensors. Okay, whereas when you look for inflation, you only look for scalars and tensors. Okay. Okay. No scaling. There is no scaling for tensor and scalar fluctuations like vector fluctuations. I'm not sure what the scaling of vector fluctuation you refer. Scaling, you mean 1/A? Is that what you call by scaling? Okay, so no, they are frozen when they cross the Hubble radius. It will be part of one of the exercises I want to ask you guys for you to demonstrate that. Let me see where I have this plot. I don't remember. when the scales corresponding to a given wavelength during inflation cross the Hubble radius, if you want the comoving Hubble radius becomes smaller than such comoving scale, these amplitudes are frozen, whereas the other ones die away, the vectors. Okay, so that's the difference.
Okay. I think we are already 5 minutes past the time.
Yeah.
Yeah, you answered many questions.
Definitely. Yeah. New message. Yeah.
Which is very good.
Yeah.
The more questions there are, the better, I think.
Obviously. Yeah. Very good. Yeah.
So
okay.
Thanks a lot for the lecture, and thanks to all the participants.
Thank you.
We meet all together again at 2 p.m. Brazil time for the Q&A. So
I will be available today online. Sorry, yesterday I thought I only had to answer through the chat in the, how is this called, the Slack thing channel, but I will be available today in this thing. And also feel free to ask the questions in the Slack channel, obviously, if you want. Yeah. Okay. Bye then. Ciao.
Ciao. Enrico, Rogerio, are you there?